The approach that we take in this course is that of statistical mechanics. In statistical mechanics, we define the Hamiltonian of a system and from there derive the partition function or the thermodynamic potential of the system. In this way, we describe every system in terms of the entropy of the system, or called the entropy representation. Now, as an example, let's take the microcanonical ensemble, where we know that the differential of the entropy, where the entropy is dependent on the number of particles, energy, and volume, is given by the first law of thermodynamics. We saw earlier that we could rewrite this equation in order to derive an expression for the differential of the energy, which then depends on the number of particles, the entropy, and the volume. And this is called the energy representation. The energy as a function of n, s, and v is then given by Ts minus Pv plus mu n, in which the dependent variables, the temperature, the pressure, and the chemical potential, are given by the partial derivatives of the energy with respect to the conjugate variable. The energy representation is the approach that is taken in thermodynamics and that we will come across in the book and in courses of other studies. In this clip, we will follow this line and develop the respective terms for the energy representation in various ensembles. The first is the so-called NTV ensemble, described by the Helmholtz free energy F. F depends on the number of particles n, the temperature, and the volume. The free energy we obtain from the energy E, which is also called the inner energy, and in the book this is referred to as U, by means of a Legendre transform. For the transform, we have to change the free parameter S in the energy to a free parameter of temperature in the free energy. Hence F is given as E minus Ts, or in the differential form, dF is equal to minus sdt minus pdv plus mu dn, from which you obtain the respective conjugate variables s, p, and mu. Another ensemble is the NSP ensemble, also called the enthalpy H. Hence, what we have to do in comparison to describing the energy, we have to interchange the parameter volume versus pressure. Again, using the Legendre transform, we know how to do this, and H then reads as E plus PV, or in the differential form, dH is equal to TdS plus VdP plus mu dN, from which you can read off the conjugate variables T, V, and mu. If we now further assume that in a certain process the pressure and the number of particles do not change, we see that the change in enthalpy is equivalent to TdS, hence the heat transfer into the system or out of the system for that process. The last ensemble to consider is the NTP ensemble, or the Gibbs free energy. The Gibbs free energy G is dependent on N, T, and P, and in comparison to the energy, you see that two of the parameters are interchanged, namely the entropy to the temperature and the volume to the pressure. Performing the Legendre transform twice, the Gibbs free energy is equal to E minus Ts plus PV. This is equal to F plus PV. The differential form of the Gibbs free energy is given by minus SdT plus VdP plus mu dN, from which the respective conjugate variables S, V, and mu can be read off. Now, in the special case that in a given process the temperature and the pressure will not change, we see that the change in the Gibbs free energy is identical to the chemical potential of the system. We have proven earlier that at equilibrium, the partition function of any system, hence also its entropy, is at its maximum. Now let's single out the energy and consider any other observable A this requires the partial derivative of S with respect to A at fixed energy is equal to 0, and that the second derivative of S with respect to A at constant energy is smaller than 0, meaning the partition function and the entropy are convex functions. The question now is, how does this translate into the energy representation? For this, we first consider the differential of S depending on two parameters A and E. So the total differential reads del S del E at constant A times dE plus del S del A at constant E dA plus 1/2 d2S by dA squared at constant A dA squared. We use here second order Taylor expansion because the second term is equal to 0 from the requirement that S is at its maximum. Now, rewriting this equation, we obtain an expression for dE is now given by TdS minus T half second derivative of S with respect to A dA squared. The same considerations we now also take for the energy representation. In the energy representation, dE reads del E del S at constant A ds plus del E del A at constant S dA plus 1/2 del 2E del A squared at constant S dA squared. Comparing the two equations in the powers of dA, we see that the first term del E del A at constant S has to be 0, and the second term we now obtain an expression for the second derivative of E with respect to A is given by minus T second derivative of S with respect to A, which now is larger than 0, as of the second derivative of S with respect to A is smaller than 0. Hence, in the energy representation, the system at equilibrium is at its minimum energy.